So I think we have the last talk for the session from Jiří Outrata from the Czech Academy of Sciences. And he will be talking about the application of semi-smooth Newton method to variational inequalities of the second kind. So I'll hand over to Jiří now.
Okay, so good evening to Australia, and many thanks to the organizers for accepting my late registration. My talk is based on a joint paper with Helmut Frerer and Jan Waldman, and it's based on a joint paper which will be submitted hopefully in the next week. The semi-smooth star Newton method has been designed or developed 2 years ago, and it's a reliable numerical tool for solving inclusions. The approximation of multifunctions appearing or arising in these inclusions is done or performed on the basis of the graph of the respective limiting coderivative. Since that time, we have solved several complicated problems via this method. And in this time, discovered Helmut actually that for a certain class, or rather broad class of mappings, this method, the original semi-smooth star Newton method, can be improved. These mappings are very amenable to the application of this method. And it resulted in a new variant of the semi-smooth method, which will be the main topic of my talk. This is the background, this is the outline of my talk. So after a short background from variation analysis, I will discuss these special mappings, which we call SCD. This is an acronym for subspace containing derivatives. And then I will explain in detail the new variant of the SCD Newton method. And finally, if I have time, I would like to describe also a test problem which has a certain economic background. So now some preliminaries. Everything is in a finite dimensional space, and we will be working with these three generalized derivatives. Excuse me, at first the cones. So having a set A and a point x bar from A, and assuming that the set A is locally closed around x bar, then we may define in the standard way the tangent or Boolean contingent cone to A at x bar via this outer set limit. And since we are in finite dimensions, the regular or regular normal cone to A at x bar is nothing else than the negative polar of the tangent cone. And finally, this limiting procedure here leads us or defines the so-called limiting or Moduchovich normal cone to A at x bar. Beg your pardon. So this picture illustrates these constructions. So for instance, if A consists just from these two half lines, then the tangent cone looks exactly in the same way, but the vertex is now, okay, I forgot to say that x bar is here the vertex. Now the vertex is in the origin. The regular normal cone is this green cone here, the northwest orthant, and the Markovich normal cone is non-convex and depicted here in blue. Since we will be working with multifunctions, we need some generalized derivatives, and we will be working mostly with these three defined here. So having a set-valued mapping F from Rn into sets of Rm, and having its graph closed around some point x bar, y bar from the graph, then the graphical derivative of F denoted in this way, df x bar, y bar, is a multifunction whose graph amounts exactly to the tangent cone to the graph of the original multifunction at the point in question. And then we will be working with the regular coderivative, which is constructed on the basis of the regular normal cone to the graph of F, and finally with the limiting coderivative, which is constructed on the basis of the limiting normal cone to the graph of F. And now this is the last definition which I need which I present in the preliminaries, and this is in fact the essential property which stays behind this new variant of the semismooth star Newton method, but also behind, I would say, most existing Newton type methods. And this is the property which we call semismoothness star. Having a set capital omega in Rn, for instance, so we say that this set is semismooth at the point x bar from omega if for every epsilon positive there is some delta positive, such that this inequality here, this one, holds true for all x's from this intersection. Here this means the delta ball around x bar, and all vectors x star belonging to the limiting normal cone to omega at x. Note that we have x here, not x bar. And if we now know what means the semismoothness star of a set, we may use the same construction like in the definitions of the generalized derivatives, and say that a multifunction f is semismooth star at this point from its graph, provided this graph is semismooth at the point x bar, y bar. And here we have a simple geometrical illustration. So assume, for instance, that our point here, it is unfortunately x tilde, but it is our x bar. So this is our point x bar. We approach this point x bar on the boundary of this set and see that this angle between this line and this line approaches the right angle. And this is in fact the essence of the semismoothness star property. And of course, you may, I would like to convince you that the same holds also in this, say, kink point. And so actually the class of semismooth star sets is rather broad. So let me proceed to the second part, to the so-called SCD mappings. SCD is an abbreviation of subspace containing derivatives, and you will immediately see why we use this acronym. In this talk, we confine ourselves to mappings from Rn into subsets of Rn. So the dimension of the original space and the image space is the same, but essentially the theory with some small modifications can be extended also to the general case when the dimensions are different. First, we define actually this graphical smoothness. Our multifunction f is set to be graphically smooth of dimension n at some point xy from the graph if this tangent cone, which is the graph of the graphical derivative, amounts to an n-dimensional subspace of the space R to n. And by OF, we denote now the set of points xy from the graph at which f is graphically smooth. And now we associate with each pair x and y from the set O of f the respective tangent space. So, and this is actually, we denote this mapping by S tilde. So S tilde assigns each x and y from the set OF the respective tangent space. And another mapping, S star tilde, is defined in this way. Here, this one is the orthogonal complement to L. And you see here a similar construction like in the definition of the co-derivatives. And so this is a mapping which assigns each x and y from OF this subspace. And we will speak about adjoint subspaces. So here we have tangent subspaces, and here we have adjoint subspaces. And the construction here has been done intentionally in order to ensure that the value of this mapping, which means the respective adjoint space, amounts exactly to the graph of the regular co-derivative if x and y belongs to the set OF. Now, in order to extend our construction also to points which do not belong to the set O of f, we consider now the space script Ln. This is the space of all n-dimensional linear subspaces of R2n, and equip this space with such a distance. Here, P1 and P2 are symmetric 2n times 2n matrices, which represent the orthogonal projection onto the respective linear subspaces. And this enables us to define now these a little bit different mappings, namely S of f at x and y is the outer limit of tangent spaces computed at the points u and v if u and v converges to x and y within the graph of f. And this is defined here. Actually, what does it mean? Actually, it should have been OF, because we consider only those points xk, yk, which belong to the set OF. So this is something like a collection of tangent spaces, limiting collection of tangent spaces. And here, in a similar way, we define a limiting collection of adjoint spaces. And okay, we can proceed further. And now this is the main definition in this section. Namely, we will call a mapping F SCD mapping, or we say that it has the SCD property at a point from this graph if the limiting collection of adjoint spaces at this point is non-empty. And we will say that a mapping has this SCD property provided it has it's an SCD mapping, provided it has the SCD property at every point of its graph. So now this is the last slide of this section, which shows actually a very simple SCD mapping. So consider such a multifunction and assume that we are sitting here in the origin. Then it can be shown that the collection of tangent spaces and the limiting collection of adjoint spaces amounts to the union of these three spaces. And it is clear from the geometry that the first one, it is this sloped or tilted subspace. Here, the vertical one is generated by this branch of the graph, and the horizontal one is generated by this part. So it's a simple example of a SCD mapping. And now we proceed to the SCD Newton method. And to explain how it works, actually, I will use a generalized equation. Generally, I could actually confine myself only to inclusions without specifying the structure of F. But we will actually work in most examples we have solved. We were working with generalized equations so that F, capital F, amounts to the sum. And we assume that small f is a C1 function, C1 mapping, and Q is semismooth star at this point, where X bar is a solution of our generalized equation. And further, we assume that this multifunction Q is an SCD mapping. The first step here actually consists in building this extended mapping where we decouple the variables in the first line. So you see we work now with two variables, x and d, and in order to ensure that this is actually equivalent with the original one, we must put here this x minus d. The purpose of this, say, expansion is actually the so-called approximation step, which I will explain in a minute. So this is the algorithm. We start with a certain point x0, set k equal 0. And then for this problem formulation, the approximation step, this is AS, consists in solving of such a auxiliary generalized equation. At the first glance, this auxiliary generalized equation might look also very complicated, and in fact, it could be complicated. But under a rather mild assumption, the solution of this problem actually amounts just a solution of a number of very simple problems under some separability structure, which is very often present in applications, and then it doesn't represent any problems. And having solved this auxiliary problem, we obtain a solution U hat and update our variables x and d in this form and put y hat, compute this one also on the basis of U hat. And we realize immediately that these variables x hat, d hat, and y hat actually belong to the graph of our expanded multifunction. Now, since U hat corresponds to the residuum of our problem, then this value you had can be used as a stopping rule. And now, if, of course, this stopping criterion is fulfilled, we stop. Otherwise, we move to the Newton step. And this Newton step actually consists in finding two matrices, n times m matrices, G and H, such that its range, so that this subspace belongs to the limiting collection of adjoint spaces of our multifunction Q, computed at this point. And if we succeed to find them, then we solve such a square linear system in variable delta xk and update our solution, put k equal k plus 1 and loop. So this is the whole problem. And now, concerning the convergence, I would first like to explain the aim of the approximation step. So first, we must ensure that these variables x hat, d hat, and y hat belong to the graph of script f. This is very simple. And the other purpose is to ensure that with some positive eta, this inequality here holds for all points xk, dk from a neighborhood of the solution. I forgot to say that if x bar is the solution of the original problem, then x bar is the solution of this expanded, augmented problem. And to state the main convergence theorem, we will need another property, namely this so-called SCD regularity. So an SCD mapping F is called SCD regular around a point x, y from its graph, provided this implication here, this one, holds true for all subspaces L from the limiting collection of adjoint spaces. So S star F computed at the point x and y. Okay, and now the convergence statement. So we assume that F is semismooth star. This is the basic assumption at the solution point of the extended system. And at the same time, it is SCD regular around this point. Further, we suppose that the outcome of the approximation step fulfills this inequality here with some positive eta. Then we claim that there is a neighborhood script U of x bar, such that if we start our iteration process at a point x0 belonging to this neighborhood, then our algorithm is well defined and either stops after finitely many iterations or produces a sequence xk which converges superlinearly to the solution. Now, concerning the linear system, which we have to solve in the Newton step, it can be shown that the SCD regularity assumption, which we have posed here, actually ensures that the matrix on the left-hand side of our linear system, which is this one, is non-singular whenever we choose these matrices H and G properly, which means in this set S star Q. Okay, so now we have formulated our algorithm in terms of a generalized equation. So these assumptions, if we are given a concrete one, then we have, of course, to check whether, for instance, this basic assumption in the approximation step is indeed fulfilled or not. Well, Now, in the title of my talk, actually, we speak about variational inequalities of the second kind. This is a nice model which has been developed in continuum mechanics and corresponds in our model the situation when the multifunction Q is the subdifferential of a certain proper convex and lower semi-continuous function small q. And in that case, here, this is the problem which we have to solve in the approximation step. So it is generally a non-smooth optimization problem. But if this Q has such a separable structure, then actually this optimization problem actually amounts to L much simpler problems, low-dimensional ones, which can be solved in most situations either by a formula or via a very simple numerical treatment. Okay, and concerning the Newton step in this case, we, excuse me, here, we may always exploit the following statement. So consider such a variational inequality of the second kind. Assume that B belongs to the subdifferential of Q at the point X. Then we claim that this multifunction Q is an SCD mapping, and for all subspaces from this S star collection, then there exists a symmetric n times m matrix whose norm is not greater than 1, and such that this subspace can be represented or expressed as the range of these two matrices. So everything boils down actually to the construction of such a matrix P, and then the linear system, the square linear system, which we have to solve in the Newton step, amounts exactly to this one. So it doesn't represent any big problem. So I actually have no time to present my numerical evidence or experiments in detail, but what I will, this is the last slide, in fact. So this is a performance profile of the semismooth star Newton method, SCD variant, in comparison with several first-order methods like forward, backward, Douglas, Radford, etc. So you see, of course, the variant which we use here has a certain globalization. It has also a scaling of the line search, but it behaves like a first-order method. But then, as soon as we reach the neighborhood from which then the Newton method start to be locally quadratic, we see a very fast progress toward the solution, whereas the other methods actually continue their behavior as first-order method. So it's a very good news concerning the numerical behavior of this new Newton variant. And finally, let me mention that these collections SF and S star F are not only useful in the Newton step, but actually they can very well be used also for instability analysis of, for instance, generalized equations or general inclusions. So in particular, they deliver or yield, on the basis of them, we can construct workable criteria for strong metric regularity or strong metric subregularity of SCD mappings. So that's all what I wanted to say. Thank you very much.
All right, thank you very much, Jiří. I guess this concludes our session, but if anyone has one or two questions, maybe we can ask quickly, because but if not,
I might have just one
Yep.
question. With the construction of the Newton step, you've got to still construct the B matrix, and you've got very few constraints on what it should be, from what I saw from your characterization. How do you go about finding this matrix?
Good. Excuse me, you are speaking about this B matrix.
Yeah, that's right. Yeah, the B matrix. Yeah.
So I think in these examples, which I wanted to present and had no time, this construction was absolutely no problem. The situation was a little bit more complicated when we tried to solve a contact problem with friction. In that case, we indeed have to work with two matrices, because it's not directly a variation inequality of the second kind. Then one has to work with two matrices instead of the one, this B, and it could be a little bit more demanding. But so each actually specific problem requires the user of this method to construct his own B or own two matrices H, G and H. And as soon as it is done, of course, the approximation step has also be checked whether it works or not. But that's all.
Just one other one while I have here. I mean, the kind of idea that you have for the for this sort of semi-smoothness, I suppose, is the co-derivative kind of really in some sense a linear subspace of some sort. That's really what is behind the construction there, isn't it? Is that what's going on here? Because usually co-derivatives, they are, they're constructed from cones, and the cones aren't really characterized by matrices and so on, but you've managed to find connect it with linear algebra in some way, these co-derivative constructions. This is so do you have any way of elucidating how you see that, how that connection works?
Okay, so at the moment, I don't know exactly the connection between the semismoothness star property and this SCD, because semismoothness star is definitely present in very many mappings which are not SCD. I am not sure if I understand properly your question, but
maybe I haven't asked it very well, but bear with me.
So the original Newton method actually could work also in the case when we do not consider a SCD mapping, but and we have, of course, semismoothness star is present. This is the essential thing in the application of this method. Whereas this is SCD, we have solved very many problems, not very many, but several difficult problems, and realized that in all of them, this SCD property was present. And so both semismoothness star as well as SCD. And this was a sudden surprise, but it has facilitated the Newton step, and a part of it, actually, this rather important role of the subspaces in stability analysis, actually not only in stability analysis, but in general local analysis of multifunctions. It was a big surprise for us.
And does this insight kind of characterize the co-derivative in any of those cases in some sense?
Yes.
Yes. And so the co-derivative then is really constructed from subspaces of some sort, and there then has some sort of inherent linear structure in it.
Actually, you are right. For this type of mappings, on the basis of these subspaces, we can, for instance, construct or prove a multifunctional variant of the Clark inverse and implicit function theorems. Because you see, this idea is somehow on the border between the Clark's theory. We use these regular points from set OF in order to come to limits, which then work also in the points outside of this set. So this is something similar to what the Clark theory does, but at the same time, we work with objects belonging to the graphs of regular or limiting multifunctions. So this comes from, say, the Moduchowicz theory.
Very interesting. Yeah. Thanks very much.
Thank you.
All right. Well, I'll take this chance to thank our three speakers again. I guess that concludes the session, and I'll see everyone hopefully same time tomorrow, 12 o'clock Australian Eastern Daylight Saving Time. So hopefully I'll see everyone there. All right. I'll stop the recording now.